polynomial functions again, specifically looking at the end behavior. We're going to be looking at the end behavior. That means the limits as the graph goes forever without bound to the right or forever without bound to the left. What's happening? And we're going to relate it to its degree and leading coefficient. That's what we're going to do today. These are kind of our key phrases there. And we'll be able to prove from it if a function is even, odd, or neither as well. I'll give you a little test for that. Very simple test. So with that, here's some vocabulary words, but I'm going to begin here. So first thing I'm going to look at is this even and odd function, the second learning objective that was listed up there. An even function is anything that follows this rule. Just box this up right there. Now that's written in math language. I'm going to translate this to a more simple math language. Let's call this proper math. That's the proper math language. And I'm going to translate this into a more simple math language. Here's what this is saying. If you have a negative x, so I'm going to put this like you've seen it your whole life as a coordinate point. If you have a negative x and this f here is positive and a positive y, if the function is even, it'll have another point that has the same x number, but this time positive, a positive x and a positive y. Let me graphically represent this. I recommend you add this to your notes here so you understand what's going on. And I'll do it with a star. This first one I'll do in blue. If you had a negative x and a positive y, what quadrant would we be in? If we had a negative x and a positive y. Not the first. Second. You would go left and up. And I'm going to put a star there. Okay, that star would be there. We don't know what x is, but we know whatever it is, it's to the left, and then whatever y is, we're up. Now I'm going to go place a star for this point. This one has a positive x and a positive y. What quadrant would that be in? The first. If we have an even function, it'll be reflected across the y-axis. You see how those? This would be your negative x. This would be your positive x. However much it is, they're the same amount, the same number. So let's just say it's a negative 4 and a positive 4, a negative 7 and a positive 7. It's the same amount, and the y stays unchanged. The y is the same. That's what makes an even function. That's the test. Okay? So that's proper math language, but that's all it's saying. Is you should have the same numerical x value, just changing from positive to negative, and the y value remains unchanged entirely if it's even. So the most basic even function is quadratic. So quadratic, what's the equation for a quadratic function? Y equals
X squared.
X squared. And so I'm going to just show you by table what I'm referring to over there on the previous chart. If I did an x and y, so just add this to your chart here. This is showing pictorially, but I'm going to show you with x values. Let's just pick a number. How about the number 2? You want to use 2? What this is saying, if it's an even function, that this statement should be true. So if I did an x value of negative 2, and I did an x value of positive 2, I should end up with the same y value. So let's take negative 2 and plug it into the equation. This is y equals x squared. What is negative 2 squared? Negative 2 times negative 2. Positive 4. What is 2 times 2? 4. Notice, are they the same numbers?
Yeah.
And this would be true for any number you pick. If you would have chosen an x value of, let's say, negative 5 and positive 5. What is negative 5 squared?
25.
25. What is 5 squared? 25. That's what makes this an even function. What makes it an even function is whether you take the positive or the negative of some x value, you always get the same y result. That's what makes it even. The only way mathematically with polynomial functions you can have an even function is every power must be even. What must every power be? Even. If you have an odd power, the math will not work out. Why would it work with evens? What does squareds do to negatives? Cancels, because it's an even number. If you have a negative and a negative. Why would an x to the 4th cancel out the negatives? Because 4 negatives make a positive. So it just have to have even powers, and it'll be an even function. Okay, so let's talk about odd. Here's what I want you to box up for odd. Here's the math symbol. It looks like I got an extra period in there. Let's translate this from proper math language to more simple math language. This is saying if you have a negative x, and now tell me about the y here. The f represents the y. Is y positive or negative there? Positive. if you had a negative x and a positive y, that would need to equal a positive x and a negative y. The example they use here for an odd function is cubic. What's the equation of a cubic function? Y equals x cubed. Okay, so let's just draw a table real fast, and we'll try this out. Here's our x, y equals x cubed. And I'm going to do the same two sets of numbers again. Let's start with -2 and +2. Let's see what we get. If you took -2 and you cubed it, that means -2 times -2 times -2. You would have 3 negatives. Is that a positive or negative number?
Negative.
Negative. And 2 times 2 times 2? So I hear some people say -6, some people say -8. You're multiplying. So 2 times 2 times 2. -8? I agree, it's -8 because you're multiplying, not adding. Okay, now what about +2 cubed? What's 2 times 2 times 2? Okay, so check out the numbers. So the x changes, and what happens to the y? The x changed signs. I'm sorry. I changed signs. What happened to the y's? Change signs. That's the definition of odd. I know this up here. I didn't do a graph. Let me go ahead and complete this to make it symmetrical, our notes here. This is saying if you had a negative x and a positive y, where would I place that star if it was a negative x and a positive y? Second quadrant, over here. Negative x and a positive y. Put a star. That to be odd, your second star, to be odd, would need to be positive x, negative y. Where is that? Down here. Odd goes across the origin. Now in our case here, we went across the origin, we went diagonal from the first to the third, which is fine, but odd functions go diagonally. Okay, so this just did that just to make the notes symmetrical, so if you compare back. Alright, let's do one more set of number. We did -2 and +2 last time. We also did -5 and +5. Let's check that out. What is -5 times -5 times -5? Negative 125. Good. And what is 5 times 5 times 5? Positive 125. Now here's what you're going to notice about odd and even functions, both of them. The numerical values will not change. The numerical values will stay consistent. I have -8, +8. The y's, they still have some value of 8. Let me say it this way. The absolute value of the numbers will be equal. Absolute value -8, absolute value of 8, they're both 8. Absolute value -125, absolute value 125. But it's still 125. Those are going to be the same. When you look at even and odd, you're seeing which ones are changing signs. When I change my x's, did my signs change or did they stay the same? If they change, it's odd. If they stay the same, the y's, it's even. When you change the signs of x's, if the y's change signs, it's odd. If they do not change, it's even. And if the numbers change, it's not even nor odd. You have both even powers and odd powers. With odd functions, you can only have odd powers. Also, you can't have a constant. So it's not odd if it gets shifted off the origin. So if you shift it up or down, it's no longer odd. Okay, so that's another key for odd to know about. The odd functions have to go through the origin. Even functions do not. Even functions can be shifted left or down because, let me go back over here. You could shift this left or down and it would still be symmetrical across the y-axis. Whereas odd functions, since they're diagonal, if you shifted it up or down, it would no longer be diagonal across the origin. So it wouldn't mathematically work out right. All right. Some examples here. Even, odd from a graph. What do you think when you look at this one? Is this even or is this odd? That's an even function. By rule, check out the powers here. What can you tell me about this power? It's an even power. And even functions can use constants. Another way to think about a constant, if it's helpful, you could put this as -1, or you could say, I don't want you to think it's a typo. It's not a typo. You could say -1 x to the power of 0. You could think of it that way if it helps. That way you know that -1 is considered even. It'll work for evens, but it will not work for odds because 0 is an even number. Since it didn't have a power of x, it's like x to the power of 0. All right, next one. It looks odd. Here's the problem. It's not an odd function. It's neither even nor odd. Why not?
Because it shifted off the origin.
That is an odd number. That's an odd number, but this is a constant. Is a constant even or odd? Come back over here. Is a constant even or odd? That's even. And so it's no longer, it's neither even or odd because you have both even and odds. You see how it got shifted off the origin? If you did your table, they would not reflect right. If you did a positive 4 and a negative 4, positive 4 is going to get a number somewhere around 2, 1, 2. If you did a negative 4, who knows? It's going to be a really, really small number you get. So it would not be the same. Yeah. Okay? What about this one? I'll let you take a look at it for a second. All right, this time, what do you think? Even or odd? Even. Now, if it's even, it should always be able to be symmetrical. It'll be symmetrical with the y-axis. Can be cut in half with the y-axis. Does that cut in half?
Yes.
Yes, this is an even function. Now, since it's an even function, it's symmetrical with the y-axis. That's kind of a proof of it. Symmetrical with respect to the y-axis. A way I remember it, as you write this down, if it were odd, it would be symmetrical with respect to the origin. The way I remember it is the O's go together. If it's odd, it goes across the origin. Can you all say it? If it's odd, it goes across the origin. Hey, quick, can you keep that up, please? And if it's even, it's symmetrical with respect to the y-axis. How I remember this is I think of your face. Put it like a hand right in front of your face like I am, kind of like this. Put your hand in front of your face. Now, when you think about this, your face is even. Why is it even? What's on either side of your hands right in his region? You have an eye on either side. You have an even number of eyes. You have 2 eyes. They're split evenly right here. What about your ears? 2 ears. They're split evenly by your hand. I would like to say teeth. In a perfect world, it would be. That's the one thing God gave us that's all over the map. Maybe someone has 1 tooth here but doesn't have the matching tooth. Maybe it's, mine aren't exactly straight. But typically your face is pretty even overall. 2 nostrils, 2 ears, 2 eyes. You can cut it in half like a y-axis. That's your face is even. Your face isn't odd. Your face is even. All right. Last thing. Look at this problem here. Even functions. If it's even, notice the end behavior, it's going to end the same way both on the left and the right. You see how both pieces are going down? That indicates the degree. This indicates the degree is even. Regardless of if it's an even function or odd function, this indicates the degree is even. If the graph goes off both on polynomials, it'll either go off to positive infinity or negative. If they go off the same direction, both of these being down, the degree is even. Remember, degree just means the highest power. It doesn't mean the other powers have to be, but the degree is even since these are both going to negative infinity. Since both, I'm going to go ahead and write the limit here. Lim f of x equals negative infinity, both when you go left and when you go right. Both when you go left and right. So I'm just going to, for the sake of time, I'm going to do it this way. Both when you go to the left and when you go to the right, the graph goes down. That means the degree is even. And we could go back and just determine on the previous functions whether the degree would be even or odd by looking at the picture. On this picture here, when you look at this, you see how both arrows are going up? Would the degree, the highest power, be even or odd? Even. What about this one? One's up, one's down. The degree would be odd. Yep, it'd be odd. Okay. So now let's look at a table view. On your calculators, turn on your calculator. Here's the main thing you need to make sure you do to get some of these values, because a lot of you haven't worked with cosine yet. I want you to go home screen, new document, and don't save. If you do that, it should reset it, I believe. You should see rad. I need you to see rad up on the top. Rad stands for radians. I'll explain that later. Whoops. Add a graph. Add a graph and type in the equations. The first one was 5 cosine plus 4. 5 cosine plus 4. 5. Press the trig button.
It says degree up here.
If it says degree, you press home screen to menu C. Menu C. Okay. Yeah, should automatically switch back. Or you can just click on it.
There you go.
Yeah, you can do one of two things. So the easiest way to switch it is like this, but I wanted to get everybody's calculators reset anyways. Since the beginning of the year, I just did that. You can just click on it, and it switches between degree mode and radian. But if yours says degree, I would want to just clear it out from stuff that we did last year, because your class, you're only using radians. AP is only going to test in radians. They're not going to use degrees at all. So I said if you press home screen to menu C, it'll clear out all the things last year that students might have used or whatever while we were doing degrees. So what was the equation here? 5. Press the trig button. There's cosine. 5 cosine x plus 4. Make sure you leave the parentheses. Our calculator automatically puts a parentheses around cosine. Leave the parentheses when you put the plus 4. Without pressing enter, I can tell you right now it's not going to be odd. How do I know it cannot be odd? The plus 4. Plus 4 is considered even. So it could be even or it's neither. Okay, press enter. Does this graph appear to be symmetrical with the y-axis?
Yes.
Okay, if it's symmetrical with the y-axis, it is an even function. Oh, that's not what we want. We wanted to fill out the table. I'm going to go ahead, since I took a picture of it. I'll just set it down here anyways. Whoops. Now, y'all press Control-T and tell me what values you get. Press your Control-T. Press Control-T, and let's get the values at -2, -1, 0, 1, and 2. Screen on your calculator. Press Control-T. I want the values at -2, -1, 0, 1, and 2. We'll round. How about we just round to the nearest tenth? Just give me the values rounded to the nearest tenth. What do you get at -2? 1.9. What'd you get at -1?
7. Do we round it to nearest tenth?
Nearest tenth.
6.7.
6.7. Okay. 0.
9.
1.
6.7.
And 2.
1.9.
Okay. Remember as we started. Notice when you compare x values that just change between positive and negative. So let's just look at -2 and +2. What can you tell me about the y's between +2 and -2 when you compare these two? They're the same. If you have the same y's when you change signs on the x, that means it has to be even. It's even because as you change your x's from positive to negative, the y's stayed the same. So that's what makes it even. Go ahead. All right, now change it to 5 sine x. To make it quicker, what you can just do is press the tab button, or if you're on table mode, you can just double click that part right there and change the equation. We want it to be 5, press trig again, sine x. Hit enter. I'm going to slide this over for my picture. Whoops. I messed up my equation there, so as you get your values in, come on. All right, what do you think on this one? Again, we'll go to the nearest tenth.
4.5. -4.5.
Fill in your values so you can tell me what you make your determination. Nearest tenth, I'm getting negative 4.5. What'd you get for negative 1?
Negative 4.2.
Negative 4.2. 0. 1.
4.2.
4.2. And 2.
5.4. I mean 4.5.
4.5. Again, if you compare any values, any x value that switches from positive to negative, if you pick any of those, what can you tell me about the y's?
Same numerical value.
Same numerical value, but they change from
Negative.
positive to negative. What does that mean it is? That's an odd function when it changes from negative to positive. Now, what's great, when it's weird when you look at the picture, this doesn't look odd, but what it means is it reflects across the origin. So if you picked any point, let's just say I picked the maximum right here. Maximum right here. If I pick this maximum, the minimum right here would correspond where the only thing that would happen is the same x value changing from positive to negative, but then the y value would also change from positive to negative. So any one of them, any maximum or minimum, would have its corresponding pair across the origin. All right, Chris, what you got? What you working on here? Make sure you're working on my stuff. All right, let's do the last one. Before you type it in, will this be even or odd or neither? What do you think? Tell me about this power. What's this power?
5.
So it has an odd degree. Tell me about this power. Even. So this is neither even nor odd. Your table should not match up. Neither even nor odd. Why is it neither even or odd? Because you have both in the polynomial. So when we graph it this time, our numbers should not match up. So go ahead and graph that in. Let's see what we get. Negative 5x to the what power? Fifth?
5.
Negative 5x to the fifth, followed by
Negative x squared.
negative 4x squared. All right, press enter. All right, when you look at the table,
Negative. You want to say the values?
sure, what are you getting here? Are your values matching up like they should if it's symmetrical? No, this is not symmetrical. If it's neither even or odd, the values will not be symmetrical with either the y-axis nor the origin. So 144, 1, 0, negative 9, negative 176. Notice they do not match up. When you compare x values that are numerically the same, just sign the opposite, these do not match up at all. So it's neither. So there's a visual approach, a table approach, numerical approach, all right there given to you. So you can compare if it's even, you should have straight across points that are corresponding, odd across the origin that correspond. Here we have nothing that corresponds across the y nor across the origin. It can't be across the x because it wouldn't be a function anymore. It failed the vertical line test if it's across the x, so that's not possible. All right, with that, let's go on to the next one here. Even or odd functions. Example 3. I'm going to give you a few seconds to think through this yourself. So I'll pick up here in a moment. Take a second to think through what you think these are. Talk about the end behavior. So end behavior is talking about what happens as the y value, what happens to the y value as x approaches the left or right bound. Meaning, for most polynomial functions, since their domains are all reals, what happens as the graph goes far to the left and what happens as it goes far to the right. If you want to write it in here, here's what we're finding. Anytime you see the word end behavior, uh-oh, my board's going out. End behavior, it's where you find the limit as f of x goes to the left. For polynomials, this is the case. And the limit as f of x goes to the right without bound. That's what end behavior is. You're going to be finding these. Now, this is not just a rule for all functions. For example, a logarithmic function won't go left without bound. The parent function of a logarithm will approach the y-axis, but it won't go to the left side of the y-axis. It won't go over there. Square root function does not go left of the origin. The parent function anyway. So all this to say, this is for polynomials that we're going to go forever left, forever right. That's what we're finding when we say in behavior. So let's take a look at a couple of these. This function here, if you want to write the in behavior, you're going to write what happens. That's kind of how you can think of limit, is what happens to the y as x goes left. I'm translating a math symbol. The math symbol is negative infinity. That mathematically means left. What happens to the y as the x go to the left? That's the first thing we're going to find. And then we're also going to find the right in behavior. The limit, what happens to y as x goes to the right? Put a positive infinity in there, meaning to the right. Okay, so taking a look at this graph. What does happen to the graph as you move to the left? And remember, a limit doesn't tell you what the graph is, it tells you where you're going. I'm really thinking y'all are distracted on other things. Unless can you turn around? Is it on this? If it's literally on this, then you're fine. Okay, you're good. Not bad. I seem a little too focused on it. What happens to this graph as we move further and further left? As you travel along this graph to the left, what happens to the graph? Here's the options. Does it rise without bound? Does it fall without bound? Or does it appear to be getting flat like a constant? It rises. So the symbol for rises or going up is infinity. And so I'll translate that. That means the graph is up or rise. It goes up. It rises. You know what? Better word than up is rise. Let me put in rise. That's better math word there. It rises. Okay, so what happens as you move to the right? If you look at the graph as you travel to the right, does it rise, does it fall, or does it get flat like a constant? It rises. So again, what symbol means rises? Infinity. And that's what in behavior is. So let's try it again on our second example. So write LIM f of x equals twice with your x arrow. While we're doing polynomial functions and even rational functions, which comes next, when we do in behavior, what will our x values be for in behavior? Our x values for in behavior. Negative infinity and positive infinity. That means left and right. Okay, on this graph, what happens? Let me go ahead and fill this in while you finish up your notes. I'll write in again. Left and right. All right, what happens as we move along this function to the left? Does this graph rise, fall, or appear to be getting constant? It falls. So what symbol represents falling on the y's? Negative infinity. You put negative infinity because this graph falls. Okay, what happens as you go to the right? That's what happens to y as the x increases without bound. What happens to y as x goes to the right? As you move to the right, this graph rises to infinity. Good. Oops. Shouldn't have said rises. We'll keep it the same. I'll just say rise. It rises. There you go. So that's in behavior. Questions on the limits? Alright. We have been doing some limits already. This time, I'm going to give you some more chance to practice. How many limits are you writing for each problem? 2. So on this page you should have 6 limits. We'll call this DOL number 2. Pause the video. I'll let you work on this one. See what you can come up with in terms of limits. Alright, picking back up. So after that round of DOLs, it says the leading term test. Now this is just telling you that if you look at the degree, the term with the degree, it'll tell you the direction of the graph. Just as I was mentioning a moment ago. So, here, if your term is this an even power or odd power if it's like an S-curve? Even degree or odd degree?
Odd.
Odd. If it's positive, it'll increase over time. Over its domain, it'll increase. If it's even, and it would go up over time. This is if the leading term is positive. Sorry. If the leading term is positive, there it is. The leading term is positive. If it's odd, it'll increase over time. If it's an even degree, they will both rise, both to negative infinity and positive infinity. This is just saying the opposite. If you're negative and it's odd, it'll decrease over time. If it's negative and an even degree, they will both decrease as you go left and right without bound. That's all it's showing you there. All right, so this one, without graphing, we're just going to come up with what we can based off this. What is my degree of this polynomial function? What's my degree here?
4.
4. That tells us, graphically, according to the leading term test, we know it's either going to both ends rise or fall. This is positive or negative? Positive. That means overall the graph, we might have 4 zeros, but we don't know. I'm just going to draw like a W. It's going to look something like this, based off the leading term of 3x to the 4th. I'm just going to say that. Does that make sense? This is, in a way, this is going to be called the leading term test. The leading term test. That's what we're going to call this. Now, truthfully, is this what this graph should look like? No. I know it needs to be shifted down one. So if I was actually going to graph it right, I would go to the calculator and do it correctly, but it will look something like that. It'll hit a -1, be like a W. So we could come up with our limits without even actually graphing it, though. Because we know this is an even degree and it's positive, we could say as we travel to the left without bound, meaning as x approaches negative infinity, or as x approaches really, really, really small numbers, very negative numbers, what's going to happen to my y values? Are they going to rise? Are they going to fall? Or are they going to approach constant? They're going to rise. And what happens as we go to the right? As the graph travels to the right without bound, the graph would rise. That's based off the leading term test. Make sense? Okay. Part B. This time, what is my leading term? Check it out. What's my leading term? Risa, what do you think? That's my degree, so what's my leading term? I'll circle up, this is my leading term. I'm just going to say LT. So based off of that, what would 2x to the 5th look like? It's an odd degree, positive. All right. So again, it's going to have some weird curves to it, but I'm just going to do like an S curve like this to be quick. Because all I care about is the leading term, or the end behavior. I'll just say y equals 2x to the 5th here. So what would happen as we go to the left without bound? Meaning as x decreases without bound, what would happen to our graph? Here, fall. Translate fall? Negative infinity. Good. When I say translate, I mean from English to a math symbol, which y'all are doing. I just want to clarify what I'm saying. Okay, what happens as we go right forever? What happens as the x's increase without bound? The graph rises. And so the symbol for going right is positive infinity. What's the symbol for rise? You got it. All right, C. Describe the end behavior of this one. All right, one more time. We got to determine what is our leading term. 6x to the 7th. Good. So you're looking, when I say leading term, what are you actually looking for? The highest power. Yeah, so if we did a quick sketch, 6x to the 7th, what would that do? It's odd power, which means like a U or like a S curve? S curve, and it's positive, so up and to the right. It increases over its domain. Might not be strictly increasing. If you remember that word, that doesn't mean it's always increasing, but over the course of its domain, it will increase. All right, so tell me about the limit. What happens as we go left, meaning as x decreases without bound? what happens to our y values? Do they rise, they fall, or get constant? Asif, what do you think?
Which one?
This one.
I was thinking, I don't know.
What happens as we go left?
Oh, down.
It falls down. So negative infinity, okay? And what happens as we go to the right? Or as x increases without bound, the graph goes up. All right. Now, the reasoning here, when it says explain your reasoning, it would be the leading term test. Leading term test. LT test. What does LT stand for? Leading term test. You got it. Leading term test. So now we've gotten into the practice. We've completed the lesson and we have some practice for you. So it looks like you have 1, 2, 3, 4, 5, 6. That's it. 6 problems to take a look at now.